inside every single gadget you own, your phone, your computer, you name it, there are dozens, sometimes hundreds of these tiny little components, and they basically work like a miniature lightning storm in a can. Without them, well, none of our modern tech would even function. So let's dive in and demystify this unsung hero, the capacitor.
So what is the connection? Well, it's pretty wild, actually. They all rely on the exact same fundamental principle: storing and then rapidly releasing electrical energy. I mean, think about it. In nature, a storm cloud and the ground act like this massive natural capacitor, right? It just stores up all that charge until, bam, it's released as lightning. Now, inside your phone, a similar thing is happening, just on a much, much smaller scale. And it's happening thousands of times every single second. Crazy, right?
Okay, so what is a capacitor officially? The textbook definition is that it's a component that stores energy. But here's the key thing. It's not like a battery. It doesn't use any chemical reactions. Instead, it holds that energy in an electric field. The best way to think about it is like stretching a rubber band. You're storing potential energy. It's a purely physical thing, and that's what gives it some really incredible advantages.
And those advantages really come down to two things: speed and lifespan. A capacitor, that's your marathon runner. It's got tons of endurance, but it's kind of slow. A capacitor, on the other hand, is a world-class sprinter. It can't go for a long distance, but it can release all of its energy in one massive instantaneous burst. And the best part? It can do that again and again and again, almost infinitely, without really wearing out.
All right, so to really get a feel for this, we got to go back in time a bit. Back to its rather shocking beginnings.
Yeah, that's a real quote from the guy who basically invented the earliest version of a capacitor, called a Leyden jar. He got such a jolt from it that he was literally like, nope, not even for the entire kingdom of France. That's how powerful it was. See, back in the 1740s, these experimenters figured out they could store a frankly shocking amount of static electricity in these simple water-filled glass jars. It was the first time they proved you could actually contain and then unleash electrical energy on command.
Now, probably the best way to really wrap your head around how a capacitor works is with this classic water analogy. So just imagine your electronic circuit is actually a system of water pipes, okay? The voltage, that's the water pressure. The current, that's the actual flow of the water. Now, the capacitor, it's like we've stretched a flexible rubber sheet, a diaphragm, right across the middle of the pipe. The water can't flow through it, but when pressure builds up on one side, that rubber sheet stretches, and in that stretching, it stores that pressure as potential energy.
And right there, that simple picture illustrates one of its most important jobs. Think about it. A steady one-way flow of water, that's like DC current, is just going to push on the diaphragm, stretch it out, and then stop. The flow is blocked. But what if the water is sloshing back and forth? Like AC current. Well, now the diaphragm will just move back and forth with it, and that sloshing energy effectively gets to pass right through to the other side. And that is exactly how capacitors are used to filter signals and smooth out choppy power.
So that simple idea of a rubber sheet in a pipe has, of course, evolved into this massive family of super specialized components. Capacitors are definitely not a one-size-fits-all kind of thing. No, they are highly engineered tools, each designed for a very specific job.
Let's do a quick tour of the main players, right? Each one has its own kind of superpower. You've got your tiny ceramic caps. They're fast, stable, and amazing at filtering out high-frequency noise. Then you have the big guys, the aluminum electrolytics. Think of them as the big energy tanks for power supplies. Tantalum and polymer caps. They're all about packing a lot of power into a really small space. And finally, film capacitors. These are your specialists, the go-to for high-end audio or high-power situations where stability is absolutely everything.
Okay, let's zoom in on the most common type you'll find everywhere, the ceramic capacitor. I mean, these things are the absolute workhorses of modern electronics. Some of them, the Class 1 types, are built for incredible precision, like being the metronome that keeps a perfect beat in a timing circuit. But most of them are Class 2, and their whole job is to be as tiny as possible while still packing a punch. We're talking microscopic. And this miniaturization is the key. It's what lets engineers put a tiny little emergency power source right next to every single chip on a board, and that is fundamental to how we make our gadgets so small and so powerful.
But like any component, capacitors don't last forever. And when they finally do fail, well, let's just say it can get a little dramatic.
Yeah, the warning signs are often really obvious, very physical. You can actually see them. See, a lot of capacitors, especially those big aluminum can types, have a liquid inside called an electrolyte. And over time, or if they get stressed, pressure can build up in there.
This is what leads to those classic signs. You'll see a swollen or bulging top, sometimes the little safety vent on top has ruptured, and you might even see some crusty liquid that has leaked out, which, by the way, can be pretty corrosive to the rest of the circuit board.
And this quote from a failure analysis really paints a picture, doesn't it? It says the electrolyte blew out as aerosol-like smoke. What's happening is that if you hit the capacitor with way too much voltage or current, that liquid electrolyte inside can flash boil. It instantly turns into a gas, and the pressure spikes. That little vent on top is a safety feature. It's designed to pop open to prevent the whole can from exploding. And when it does, it releases that pressurized gas in a plume that looks just like smoke. It's pretty spectacular in a bad way.
Believe it or not, this whole failing process is so predictable that engineers have a name for it, the bathtub curve. And it makes perfect sense when you look at it. You have a few failures right at the beginning. Those are just manufacturing defects, infant mortality. Then, you have a long, flat period of useful life where failures are super rare and random. But eventually, things start to wear out. The internal materials degrade, and the failure rate starts to climb steeply. For those electrolytic caps we talked about, it's often because that liquid electrolyte just slowly evaporates over years and years of use.
So, with all that in mind, how does an engineer actually choose the right capacitor for the job? It's not just about grabbing one off the shelf. It is an absolutely critical decision that directly impacts how well a device works and for how long.
Let's look at a really common trade-off an engineer has to make. You've got your standard, classic aluminum electrolytic capacitor. It's cheap and it stores a ton of energy. Great, but it has higher internal resistance. Engineers call it ESR, which basically means it's a little less efficient and wastes some energy as heat. Then you have the option of a newer aluminum polymer capacitor. It uses a solid material inside instead of a liquid. The payoff? A much longer lifespan and super low ESR, which is fantastic for high-performance gear. The catch? You guessed it. It costs more. So where are all these capacitors actually going? What are they doing? Well, as you can see here, the biggest job by far, almost half, is for something called decoupling. That's where we put that tiny, super-fast energy reservoir right next to a chip to give it that instant shot of power it needs. The next biggest chunk is bulk capacitance. These are the big water tanks, the ones that smooth out the main power for the whole device. And the rest? Oh, they're busy filtering out noise, helping create timing signals, and doing a dozen other critical little jobs all over the board.
So here's the crucial takeaway. The number you see printed on the side of a capacitor, its capacitance value, that's just the headline. It's only the very beginning of the story. A good engineer has to juggle all those other factors. Its stability, its lifespan, its internal resistance, its size, all of it. They're balancing this entire equation to pick the absolute perfect component for the job.
Okay, and finally, let's look to the future. Because there's a new class of capacitor that's starting to get so powerful, it's seriously blurring the line between what a capacitor is and what a battery is.
Say hello to the supercapacitor. We're not talking about microfarads or even millifarads anymore. No, these things can store thousands of farads in a single component. That is a truly colossal amount of energy, and it's getting them into the same league as batteries when it comes to energy density.
But here is the absolute kicker. They still have all the advantages of being a capacitor, not a chemical battery. Just look at this comparison. A supercapacitor can be fully charged in seconds, not minutes or hours. Its cycle life? We're talking around 1,000,000 cycles, not just the 500 or so you get from a good lithium-ion battery. And its power delivery, that sprinter-like ability to dump all its energy at once, is just on another level, an order of magnitude higher.
Now, to be clear, they're not ready to replace batteries everywhere. Not just yet. Their energy density is still a bit lower, but the technology is getting better all the time, and it really makes you wonder, right? What happens when you can recharge your electric car in the same amount of time it takes to fill up a tank of gas? What becomes possible when we have energy storage that basically never wears out? That's the incredible future that this tiny unsung hero is helping to build.